So on Tuesday, we talked about inverse functions, just conceptually what they are. And the reason why we did that is because this entire unit is covering exponentials and logarithms. Those are inverses of each other. So we spent Tuesday talking about the concept of inverse functions, but really then we're just going to put that idea on hold and refer back to it sometimes, because we're going to spend the next several lessons just exploring exponential functions. So this was more like an intro idea. And the things that we talked about for inverse functions was first a couple things. Well, first I want to say actually, when I say an inverse function, it kind of means, it basically means the x's and y values are just switched. Okay, that would give you a different graph, that would give you a different function, but that's what's going on. Their x and y have switched places. And what happens in that case is if something was a function and passes the vertical line test, in order to be an inverse function, or something we call one-to-one, we also want it to pass the horizontal line test, which works exactly the same way. A horizontal line anywhere on the graph would pass through only one point. And that is something that we would call that one-to-one, because there's one x for each y and only one y for each x. Whereas when it was only the vertical line test, like this passes the vertical line test but not horizontal, in that case there's one y for each x, but there could have been two x's for each y. I apologize if I said that wrong. I think you understand, but you get what I'm trying to say. So we, on the homework and the notes, we said yes or no if these passed both tests. If no, explain why. Yes, there's problems like that on your quiz. And then what we did was, on these two notes, algebraically found the inverse function. And on the back, we proved it using composition of functions. So this is going to be the most dense part of everything we do today. So just sort of listen. I'm going to do all of those concepts just on this one problem right here. It says find the inverse of f of x equals x cubed minus 5. Well, if this was just a table, an xy table, and I was asking you to do the inverse, all you would do is switch the x's and y's. But that's not what, or if it was a graph, we would reflect it over y equals x. But this is a function, so the inverse needs to be in the same form. It needs to be an equation. And these are the steps for doing that, okay? The first thing is that you use y instead of f of x. And the reason why is because we're going to switch the x and y. So I need a y there. And f of x is just something we call function notation. It's the name, and then that tells me the independent variable. And it doesn't even have to be f of x. It could be g of t. Okay, these are both equivalent functions, just with different names and different variables. But x is generally the independent variable, and y is the dependent. So step 1, use y instead of x, instead of f of x. Step 2, interchange x and y. So here's where I do the exchanging them. I don't change anything else. Y becomes x becomes y. Okay, but I want to find the inverse function, and when we define functions, it's always like y equals something. Right now I have y being cubed and then a minus 5, so I need to get y by itself. I'm solving for y, so I add 5 to both sides. X plus 5 equals y cubed. And then from here, to get y by itself, what's the inverse of cubing something? Cube rooting it, right? That's how you would undo that. So I cube root both sides. This cube and this cube root cancel out, bless you, leaving me just y, which is fine, except the last step says to now put your function notation back in for y, but I can't call it f of x again, because that would imply it's the same as the original f of x. This is the notation we use for inverse. F of x is the original. We put a negative 1 up here to show it's the inverse. It doesn't mean f to the negative 1. It's not an exponent properly. It just means the inverse. Okay? And so that's all this problem was asking us to do. However, on the back of the notes, we are practicing one, a concept called composition of functions, and two, verifying that the inverse is accurate, that it works. Now here's a sort of intuitive way that you can check if maybe your math was correct. It's not 100% foolproof. You can't actually rely on it every time. But in general, the original function had a -5 and a cube, and the answer has a +5 and a cube root. So it kind of feels like we did it right. But we can also use algebra to see exactly whether or not it's correct. And this is a two-part process. Okay? The first part is taking the inverse, plugging it into the original. Math, 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 you should get just x, because everything cancels out. And then vice versa. You take the original, you plug it into the inverse, math, 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 you should just get x. It is a long process. It's tedious. You're not going to have to do it too often, but I think there is one problem, at least for sure, on your quiz. And so what I'm about to cover is this concept that was on the back of the notes. I'm going to do right here for number 2. On the back of the notes, it talked about composition of functions. Here's what that means. A composition means one function is the input for another function. So because like normally with this original thing right here, if I asked you to find something like, if I said, what is f of 4? What would you do here? What does that mean? X is 4. Okay? The input is an integer. The input is a number. But when I say a composition of functions, the input now is going to be the entire equation. Okay, so I'm going to do this two different directions. The first direction is the inverse function is going to be the input of the original function. So instead of putting 4 for x, I'm putting that entire thing for x. And this is what that looks like in notation. F of the inverse function. Okay, so instead of f of 4, I have f of the inverse. So when I plug that in to where x cubed is, I have all of this thingy here. That is replacing x, and x was cubed. Okay, I substituted this whole thing for x, and x was cubed, and then there's a -5. Okay, so now we're just going to simplify. That cube root cancels out, or the cube cancels out the cube root right here. Boom, boom, leaving me x plus 5, -5. The 5's cancel, leaving me x. That's what I wanted, because that proves that everything cancels out. By the by, when you have a quiz or test this unit, please do not put nonsense here and then write x check, because I'm checking your math, okay? I'm going to be checking. You see where I'm going with that? That happens quite often. Just nonsense, 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 x check? No. I'll be checking your math on that, okay? And then, so that was here being plugged in here. We also have to check this one being plugged into this one. And so that, as a composition notation, would look like this, meaning we're plugging f of x into the inverse. So I'm taking x cubed minus 5 and putting it right here for x. Okay, all that other stuff stays the same. So I have the cube root of x, which is going to be x cubed minus 5, and then plus 5. Now here's the thing about this one. This one is tricky. I'm going to put this in black so that you know this is evil and bad. I cannot do this right here. Okay, those cubes do not cancel each other out, because only this x cubed is cubed. Minus 5 is still under the cube root. Plus 5 is still under the cube root. So you haven't actually canceled anything. Now, on accident, that will give you the same answer. On accident. But I'm still circling it for partial credit because it's bad math. What you have to do instead is start simplifying under the radical. The way it's written here, the minus 5 and the plus 5 cancel. Let's see. That's not evil. I just accidentally didn't put it in blue. And so then now you have the cube root of x cubed, which is x check. Okay. So did y'all survive that? It's not really hard, right? It's tedious and long, but you can do it. You can do that. Any questions about that stuff? All right. Yesterday's lesson is very similar to today's lesson. Yesterday we started graphing exponential functions. This y equals b to the x is the basic form of exponential equations. And the reason why it's called an exponential function is not just because it has an exponent, because quadratics have exponents, and we don't call them exponential functions. An exponential function specifically has an exponent with a variable in it, okay? And their graphs look like these. It's either increasing for when b is greater than 1, or it's decreasing for when b is less than 1. And b stands for any number. Okay, that's just the base. Like I could have, like here are some examples of exponential functions. Y equals 5 to the x. Okay, b is 5. Y equals 7 to the x. Y equals 1/2 to the x. Okay, so the base can change. And it changes the shape of the graph only a little bit each time. Well, from the beginning. Later it changes, like as x goes out to infinity, it changes differently. But that's what the basic equation is representing. And these two cases down here, the reason why they're specified, like when b is greater than 1 and b is less than 1, because when b is greater than 1 and you're putting an exponent on there, it gets bigger and bigger and bigger. Like you hear people say it, they multiplied exponentially or something like that. As x gets bigger, the y goes bigger and bigger and bigger. Down here, when b is less than 1, like let's say it's a fraction, like let's say it's 1/4. So 1/4 to an exponent means 1/4 times itself that many times, right? So what's happening is, like, let's say you had 1/4 to the third. Okay, that's 1/4/16, 1/64. That bottom number is the thing that's getting bigger and bigger and bigger and bigger. But what happens when you're dividing by bigger things? The actual value is doing what? Decreasing, getting smaller and smaller and smaller and smaller. And so that's the reason for the two different scenarios, okay? But they do have some things in common every time. And those are listed here. The domain is always all real numbers. The range is from 0 to infinity, because no matter what you plug in for x, that will never actually equal 0. Will never hit 0. There's no x-intercepts because it never crosses. There's always going to be a point here at 0, 1. No matter what your base is, because no matter what you put here, if x is 0, anything to the 0 power equals 1. So that 0, 1 is on every basic exponential graph. Another point that's kind of sort of the same on every graph, the concept is the same. When x is 1, the y value will be whatever your base is. And that makes sense too, because if you had 5 to the x and you put in 1, then point's going to be 1, 5. If you put in 1 for x here, your point's going to be 1, 7, and so forth and so on. So 1 comma, whatever your base is. And then a horizontal asymptote right here at y equals 0. So we've got 0, 1, 1, whatever b is, and then this asymptote at y equals 0. Those are the three key features to look for every single time you're doing an exponential graph. And this one has the same. It has the horizontal asymptote. It has 0, 1. And it's 1b this time because b is less than 1. It's lower down. It's smaller. I'm not going to do the examples on this notes because today's lesson is an exponential function and the transformations work the same. It's like transformations we've always done. You get the basic graph in, you just transform. So keeping all this in mind, we are now doing today's notes. Was there any homework questions? I'll get back to that in a second. So notice that today's notes, it's an exponential function because the exponent has a variable. What's the base here? What's in place of the B? E. And that is not a variable. It represents the transcendental number E, hippie number. Remember we talked about that at the beginning of the year? And I'm going to show you this video. It's very short, but it sort of explains where E came from and in what places it's like important.
About pi, the ratio of a circle's circumference to its diameter. But there's a less famous but equally fundamental number known to anyone who's taken high school algebra. It's about 2.718281828459045 and so on. And it was first defined by Jacob Bernoulli, but later Leonhard Euler called it E, and the name stuck. Bernoulli first defined E through compound interest. Now, compound interest says that you get a little bit of money in interest every period, and that money you gained helps you gain even more interest next period. In other words, your interest compounds. So if you stick $1 into a bank account with a 100% interest rate compounded annually, you'll get $2 at the end of a year. If it's compounded semi-annually, you'll end up with $2.25. Quarterly, and you'll end up with $2.44. Monthly, $2.61. Weekly, $2.69. See where we're going? If you increase the number of compounding periods a year towards infinity, then you'll get closer and closer to E dollars. In statistics, it describes the most important statistical distribution, the normal. In biology, it models populations of species through the logistic function. In physics, E describes the exponential decay of a radioactive material. So while E may not be as famous as pi, it's easily as fundamental and immensely important.
The number pi is equal to 3.141592653 and so on and so on. And it represents the ratio of any circle's circumference to its diameter.
We explain how Archimedes chose pi.
So I don't know if y'all ever think about this kind of thing, but like whenever I see those, did you see the formulas at the end, like for the different fields and stuff? You know, way back when there was just early man, like we had to come up with numbers and symbols and formulas and ideas, right? Like if we were just existing here, like if you just plopped us on the earth without all the stuff we already have, how long would that take to come up with these kind of things? It takes like a long time. And to think that those kinds of crazy looking formulas represent things that happen naturally in nature and somebody actually came up with it or found enough data and was obsessed enough and loved math enough to come up with that thing. Or like if you think about E equals mc squared, that is such a simple, short, elegant, beautiful formula. And it's very complicated. And humans just came up with that. I mean, humans are amazing. And they can also run a mile in 4 minutes. And so they're like amazing on all kinds of levels. I mean, it's way higher than my pay grade. I'm not coming up with it. Coming up with stuff like that. That's kind of crazy. It doesn't actually, that stuff doesn't actually exist in the tangible world. You know, you can't touch stuff. I don't know. It's crazy. All right. So that's the coffee. I just have my coffee and I'm blabbering. All right. Y equals e to the x is a exponential function. The base is e. About what does e equal? 2. We're going to go with 2.7. All right. We're going to let e be 2.7 for graphing purposes. Okay. We're not going to graph 2.71281818 or whatever. That's just do 2.7. So this is exponential. E is 2.7. What two things are the same on this graph as every exponential function? The two things are exactly the same. What's one? I heard y'all. The 0, 1, and the y equals 0. And then for this particular graph, its additional point at 1, what would the y value be there? When x is 1, y would be 2.7. Because it'd be actually e. How do you graph e? You don't. You graph 2.7. Approximately. And so we're going to do some transformations of this graph, and we'll be focusing on that asymptote and those 2 points. Also, to the right, I have the order of transformations. I didn't really have room to put this on your notes yesterday, not in any way that was aesthetically pleasing, anyway. But I do recommend that you memorize the order of the transformations. 80% of the time, you could not care about the order and still have the right answer. But anytime that there's a vertical reflection, the order matters. So it's a good practice to just do that order every single time, so that you don't accidentally mess up somewhere. Horizontal shifts first, reflections second, and then vertical shifts last. And there's two kinds of reflections. One where the negative is in front of the x. Remember, that means it's a reflection over y. And one where the negative is out front of the function. That means it goes over x. So in these two examples, and just real quickly, in case you have a hard time memorizing which way the reflections go, if you just think about it, what's happening in this one, the negative x, is instead of x being 2, now it would be what? Negative 2. Which way did that go? It went over the y-axis. Same thing here. If your value here was 4, but now you put a negative in front, that's y equals 4. Now it's negative 4. It flips over the x. So if you have a hard time memorizing those, if you can remember the concept of it, it might be easier. So here we've got y equals e to the x plus 2 minus 3. If you did not do yesterday's homework or look at the notes yet, one of the things the problem asked was to identify the basic function. What is the basic function here? Y equals e to the x. And I kind of want to bring this up because in talking about yesterday's stuff for just a moment, because yesterday's stuff had actual numbers for bases, like literal numbers. This is not a stretch by 5. That 5 and that e are not a values. Okay, so these work a little bit differently. Like we're used to, if there's a number out front, it's some kind of stretch or compression. That's not happening on these. That base is sort of a basic component. It's not a transformation. It's part of the basic graph. And so when I say what's the basic graph here, it's y equals e to the x. E is part of it. If an exponential function had an a value, it would look something like this. That would be an a value, okay? But we won't be doing those. Not right now anyway. So in this, let's go ahead, if you haven't already, just graph that basic function e to the x. We have y equals 0 here, 0, 1, 1, 2.7. This is the basic, and then we'll do the transformation. There are two transformations happening here, okay? There's a plus 2 with the x and a minus 3 on the outside. So we're doing anything that's plus or minus to the x, you're doing that first. That's your horizontal shift. It also happens to be the insider's lie. So in this case, if I'm doing the plus 2 first, what does that mean? Which way am I going to go? Left 2. And then the minus 3 means down 3. So the good news about this is just transformations like we've always been doing. So we take our 0, 1, we go left 2, down 3. And then we take 1, 2.7, we go left 2, down 3. Which way do you think my horizontal asymptote is going? What do you think? To the right? Moving it to the left or right doesn't really change anything. Down, right? Down 3. So one thing I want to bring to your attention is the only time your horizontal asymptote changes is if there's a vertical shift, because the y values are changing. And that's going to force this up or down. The left or right shift isn't really going to change it. It's still in the same place, technically. But only a vertical shift will put it up and down. It's going to be down 3. and it's down 3 because of the minus 3 at the end. So you try number 2, please. Do both the basic graph and the transformed one. You can use 2 different colors if you're a color person. You can do dashed and solid. I was going to say dashed and dotted, and then I realized that's the same thing. Bless you. All right. So the parent function, who's comfortable with the parent function? Raise your hand. You got the basic done? Okay. So we have this, we have this, and we have this. I think y'all aren't trusting yourselves is what I think. You're sort of thinking too much and then you're quitting. Let's just do this like one thing at a time. What did you first? Okay, excuse me. Did you do the asymptote first or points first? What did you do? Points? So mostly points? We'll do points first. The transformations are, so there's a negative in front of e to the x. Is that over y or over x? Okay, over x. When the negative's out front, we know it's going to go over x. There are no horizontal shifts, so we know we're going over x first. And then plus 2 means, or that plus 2 means what? Up 2. Okay. All right, so this point, 0, 1. Here's what it looks like to go over x. That's a placeholder right there, okay? Over x means it's a mirrored reflection. If it's 1 above, it's got to be 1 below. And then I have to take that point and have to go up 2. Well, where does that get me? Same point. That's all right. Okay, that means nothing. That doesn't mean you're doing it wrong. This point at 1, 2.7, if I'm reflecting it over x, instead of 1 comma 2.7, it's going to be 1 negative 2.7. So let me do that. And when I'm up here at the smartboard, I get all cross-eyed with these graphs. So that's just my placeholder point right there. And what do I have to do at that point now? Go up 2. 1, 2. Okay? Who got that point? Okay? What am I going to do with my horizontal asymptote? Move it up 2. This determines where your asymptote's going. Okay, because that's a vertical shift, and so it forces it up or down. So now that's going to go up 2. And then you may be kind of like, I don't really know what's going on here. But think about it. If this curve is a reflection, and I have this curve, I'm reflecting it over, it's going to be opposite what it was. It's going to be going like this, just shift it up. So this is okay. Yeah? Okay. It's kind of no big deal. It's practice. And trust yourself a little bit. And that's what erasers are for. So use pencils. In case you try something and you get it wrong. This section down here on your homework says, use a calculator to evaluate blah, blah, blah. Just cross that out. I don't even care about that. And in this new seat arrangement, when I'm passing out papers, just pass them straight back. There's been lots of confusion today, like they passing to the left, right? I didn't realize to clear that up. Oh, I think I'm still recording.